Hello, everyone. Lecture 11, Molecular Geometry, Polarity, and Valence Bond Theory. We will cover in this lecture, which has two parts. This is the first video, Molecular Geometry. In the second part, it will be Valence Bond Theory, hybridization. And then the week after, we will finish everything with polarity and intermolecular forces. That's at the end of your lecture right here. That's the end of the material for the semester. Let's begin. I'm going to briefly go over a little bit of the theory just to understand, show you what I mean using a simulation, but we'll spend most of the time working on problems of Lewis structures and determining their molecular geometries. So let's begin. The molecular geometry of molecules is an important characteristic that affects the reactivity, polarity, and biological activity of molecules. So just to give you an example of this is the sense of smell. The sense of smell, which I'm going to write here, operates on the idea that you have receptors in those cells, and those receptors, when they bind to, or the molecule binds to them, there's an electrical signal. We call it electrical tunneling, right? It goes from one side to the other, and based on that structure and that geometry, the signal is sent to the brain, which is interpreted as a smell. It creates this aroma in your mind, really, and that's the sense of smell. So it's critical, very important. So Lewis structures assist us in understanding the composition of molecules of their covalent bonds. Yes, that's what we did in Lewis structures. So this was a Lewis structure for methane. We knew what bonds we have, single bonds, any lone pairs, whether we have triple, double, all of that stuff. So they show us the number and types of bonds between atoms. However, they don't actually show us the overall shape of the molecule. This molecule looks to you as if it's flat. This is in two-dimensional. You know, we live in a three-dimensional world, so molecules have a three-dimensional structure. And basically, here's a structure of methane. Methane looks like a pyramid, if you think about it. So if you see this in 3D, you see that you have carbon in the middle and the hydrogens on the outside, and they are at a 109.5 degree angle. So there's an angle here. There's an angle there and there, and in between, that angle is 109.5. So to show you this in a better fashion is this simulation that I will refer to it a lot. So hopefully you can see this from your view and notice that this is the structure of methane. Here's carbon in the middle, and those are the four hydrogens. And again, notice how it has what we call a tetrahedron or a tetrahedral structure. Tetrahedral means it has four faces. And if you look at it, it does have four faces. Not sure how you see it from here, but here's one face. Here's another face. There's a face on the bottom and the face in the back. So if we refer back to this, you'll see that it has four faces. So that's actually the three-dimensional structure. where does it come from? Why isn't it a flat molecule? Well, it depends on something we call a bond angle. A bond angle. The bond angle is actually what determines the overall shape of the molecule. It's this angle right here. You see it, the 109.5. So in methane, as we said, each carbon-hydrogen bond right here, each carbon-hydrogen bond has a 109.5 degrees angle. Okay. So here's how we draw. So this is your bond angle right here. Or here. You see the angle. 109.5, 109.5, 109.5, since you have 4 angles here. How do we draw this structure? I'm going to show you the way of drawing this structure, because we will use this all the time. So for tetrahedral, for example, because it's really the most important shape, especially when you get to organic chemistry, and that angle is the most important one. What you do is you need to use, you put a carbon in the middle, and then the hydrogens are going to have to be distributed around. But we can't just show them as we did here, because that wouldn't do it. That's a 90 degree, it looks like it. So what we do instead is we use 2 representations here. We use a solid wedge, and we used a what we call a hatched line like this, or a dashed line. I guess some people call it dashed, but it's actually hatched. The solid wedge, and I'm going to show you, mean this is pointing toward you. It's easiest if I say toward you rather than say in and out, all that stuff, toward you. And then the hatched line is away from you. So I'm going to draw this and then show you on the simulation. So here's how we draw it. And don't worry, you're going to have a sheet you can use to draw this, so not an issue. You put a hydrogen, and then you put an angle that's close to 109.5. And then what you do is put a solid wedge. By the way, this can be shaded, or it could be left like this for just ease of drawing this. And you put an H, and then next to it, you put a hatched line with an H attached to it, like this. Okay, so this actually is a tetrahedral molecule. Okay. Or basically right there. You see it? Anything as close as possible. So if we try it again, it would be like this. And that would be tetrahedral. So the angle here is 109.5, 109.5, and in the back, etc., all around. Okay, so here it is. Imagine if you're holding it like that, like this. Here's the solid wedge. Here's the hatched wedge or line. So you see it pointing away from you. This is pointing toward you. Very well. So this comes from what we call VSEPR, or Vesiper, which is valence shell electron pair repulsion. So it's a universally accepted model for the prediction of molecular shapes and geometries. We use this model to help us. And what is an electron domain? An electron domain, and this is a very important definition, basically a domain means nothing but a group of electrons. A domain consists of non-bonding pairs, single or multiple bonds, and the sum of them all called steric number, and we're going to need to use this also when we get to the valence bond theory. But what do I mean by this? So if we look at ammonia, Ammonia as a Lewis structure looks like this. See, this is the Lewis structure. And by the way, we need to be good at Lewis structures in order for us to be good in this topic. This topic depends 100% on your ability to draw the correct Lewis structure. So here's the Lewis structure. So we have, let's see how many domains we have. We have 1, we have 2, we have 3, and we have 4. How come? Well, this is a non-bonding pair. This is a lone pair. So that's one domain. And these are all single bonds. And you have 3 of them. So you have 3 of them, and you have one lone pair. All in total is you have 4 electron domains. So you have 4 groups of electrons. This is one group, 2, 3, and 4. Now, when we get to double and triple bonds, they are also 1, because you can have a group of 4 electrons, a group of 2 electrons. Single bond, double bonds. That's what we mean. Okay, so we'll get back to this, but the idea of it is, why do we get an angle to begin with? What's the point? So the reason why is because electron domains are negatively charged, so they repel one another. You know, if you have a negative and the negative, they repel each other. They don't like each other. So if they get close, they cause instability. They move it around, the kinetic energy, not good. So you need to keep them away from each other. Okay, so you gotta keep them away. And how do you do that? Well, you have to fine tune it to a certain angle where that angle minimizes the repulsions among them. And that's the basis of the VSEPR model. Okay, so here they are. These are the models. And then we're finally going to jump now to the molecular geometry. But just to give you an idea of the theory behind it is, let's just go back to, okay, so let's begin. If you have 2 bonding pairs, 2 electrons, you can't have, you know, just like this right here. In fact, you can have 1, but we're just going to begin with this. If you have 2 bonding pairs, think about it. What is the best way to keep them away from each other? Because this one right here and that one, they repel each other. The best way is to keep them what? 180 degrees away from each other. All right. Notice that as I'm trying to kind of bend it, bring it close, the angle is decreasing. So look what I'm doing here. The angle is decreasing, but if I try my best, eventually they're going to go back to 180 because those electrons do not like each other. So watch again. So here I'm trying to bend it. They went back. They have to be away from each other. And that's basically where you get 180, and we call this linear. Okay, what about if you have 3? Okay. Well, the best way is, let's say you add another one. Here's, let's say, the other one, or the one you added. Not sure which one it was, but let's do it again. Here it is, this one. Notice now, okay, you can't afford a 180 because you have 3 electron domains. So the best way is to keep them 120 degrees away from each other. This is the best way to minimize it. So if I try to shrink this angle, it's going to go back to 120. Remember, electrons repel each other. And that's what we mean by this one. The third one, here's the angle. Here's a predicted, the angle, and here's what we call the electron domain geometry. It's called trigonal planar. So here it is, trigonal planar. You can also talk about trigonal molecular geometry. We're going to get to them soon. Now, what about if you have 4? Okay, well, that's a 109.5, the one we talked about. Not 90. 90 is bad. This is the most important angle in organic chemistry. In fact, the stability of things is judged by this standard. So here, again, trying to shrink it, nope. Or even extend it, nope. Still going to go back to 109.5, which is what we call tetrahedral. And that's the angle right here. Now, what if we have 5 and 6? Sure. Okay, so with 5, notice now we have an interesting structure here. If you notice, these are 90 away from each other, like this one and that one right here. But in between, you have 120. So, and the name of this is called Trigonal Bipyramidal. The reason why it's called Trigonal Bipyramidal is because you have a trigonal. Trigonal means, you know, from 3 base, like a triangle base. But it has 2 pyramids. Okay, what do we mean by the 2 pyramids? So let me show you. Okay, this is not helping me. There we go. So if you trace this, you have a pyramid on the top and you have a pyramid on the bottom. Like here, maybe this picture is better. Here, you see the pyramids, the 2 pyramids here? Here, you see the 2 pyramids. That's why it's called trigonal bipyramidal, 2 pyramids. And then the angles are 120 and 90. And then finally, if you have 6, that's called an octahedral. Octahedral means, octa means 8, hedral means face, means it has 8 faces. And you see that it's all 90 degrees. These are the possible structures of molecules. Of course, we're going to have some deviations when it comes to molecular geometry or molecule geometry. So meaning that if I remove 1 and add now a lone pair, okay, things are changing. And that's basically what we're going to do now. Very well, that's the basis of it. So let's move. Here are the molecular, so we're going to focus on molecule geometry or molecular geometry. You need to be able to draw the Lewis structure correctly and then figure out the geometry based on a simple method that I'm going to show you. Number 1, be good with Lewis structures. You have to know your Lewis structures as good as you know your name. It's that imperative. So make sure you're good with your Lewis structures. Do enough of these, because once you get the Lewis structures, all you have to do is use this sheet and you're done. Do some one simple thing and you're done. It's really that simple. Of course, you still have to understand, you know, like what does this structure mean? How does it look like? But getting to that point is dependent on you drawing the correct Lewis structure. So notice that you have all kinds of structures here. We're going to do as many as we can, but it all follows. So let's begin. So what I need you to do is I need you to have a periodic table, and I need you to take out this sheet right here. This was given to you in the handout. It's called the AXE sheet, AXE sheet. It's for the VSEPR. You need this one. It's in your handouts. It's the one with the periodic table and all the other stuff. So make sure you have this out. Very well. Watch how simple this method is. So you need to draw the Lewis structure. Now, we are going to draw Lewis structures, but I'm going to rely on the idea that you've practiced enough. So let's start with something very simple. CO2. Now we drew CO2 before, but you know, carbon has 4 valence and you have 2 oxygens, 6 and 6. That gives you 16. Carbon is central. Oxygen's on the outside. you have to give the outside the octets. After all, carbon is not happy. So what do you need to do? You ran out of electrons because you have 16. You have to do double bonds. So we knew why we needed 2 double bonds because of the formal charges. So once again, everything is connected. So you get this structure right here. Very well. How do we use the axe method? Okay. You ask yourself, what does axe stand for? A is a central atom. Now this is always 1. Okay. So you only have A. You can't have A2 or A3 or A4. No. So this is your A. So I'm going to use a different color. That's A right here. X is the bonding electrons or bonded atoms. Well, how many atoms are around the central atom? How many atoms are around carbon? You have 1, 2. 2 atoms, X and X. Okay. E stands for electrons. How many non-bonding pairs or lone pairs on, of course, on the central atom? And by the way, you can also do each atom by itself, but we'll get to that later. Well, do you have any electrons, any lone pairs on here? Nope, no lone pairs. So that means E is 0. We don't care about it. Okay, so what do we have here? We have AXX, so that's AX2. AX2. Okay, let's go, and let me erase this because we need to be able to draw here. Let's go now to our sheet. Find AX2. Here it is. AX2 is called linear, and the angle is 180. So this is called linear. Here's the angle, 180. And the geometry is called linear. That's it. So visualize it. It's a flat molecule, 180 between this atom, oxygen, and the other oxygen. Okay. Let's go to CH2O. Okay. C is central, 4 valence, 2 H's, 1 each. You're going to need a lot of space. Unless you just want to draw the final answers. And 6 valence. So that gives me 12. Notice that a lot of these we drew before because they're very common. So C is in the middle. We have 2 H's. Okay. So outer atoms first, you put the electrons. So then in this case, C is not happy because it doesn't have 8, it only has 6. So what do you have to do? Double bonds, right? So you're going to have to do a double bond between the carbon and the oxygen. So it comes out to be this. Okay. So we're done after they have 8, unless it's a one of those exceptions that we talked about, exceptions to the octet. Then you go ahead and move on to the geometry. Okay. A is the central atom. Well, here's A. How many atoms are surrounding carbon? Hydrogen, hydrogen, and oxygen. So that's A, X, X, and X. Are there any electrons on C? That's what E stands for right here. Any lone pairs? No. on C. So therefore, we have AX3. Okay, let's go find AX3. Here it is. AX3 is called, and it's pronounced trigonal, not trigonal, trigonal or triogonal. No, it's called trigonal planar. Trigonal means 3. Planar means it's in the plane of the paper. So trigonal planar, and the angle is 120. How do you draw it? You want to draw it at this. If you're asked to draw, you draw it at this, just like this picture. So let's go and redraw this. So it looks like this at a 120-degree angle like this. All of these are 120 degrees, and that's called trigonal planar. Okay. So let me show you some of these molecules. Here's CO2. You saw the 2 double bonds. The molecular geometry is linear, and here's the angle, 180. And now we may not have this one, but we may have something similar to it. If not, we can just, so BF3 is also trigonal planar if you were to draw it. And here it is. This is what trigonal planar is. Notice how flat it is in the plane of the paper. And it's 120. And this is, by the way, on, if you would like to see it, I'll post it for you to use. It's under PHET, FET. It's a wonderful website for this stuff. Okay. Next. So let's say we want to draw SO2. So you should be able to draw it. You can pause right now. And we can draw it together and find it. Okay, so the structure of this comes out to be okay, well, why? Because S has 6, O. This is 18 valence. So you need a double bond. And you know you have resonance in here. So remember, this has resonance in it. But you can do just the molecular geometry on one of them, on one of those resonance structures, because this double bond can switch. Okay, so wonderful. Let's begin. A is right here. We have 2 X's, 2 atoms on the outside, the 2 oxygen, XX. And now E right here is, do you have any lone pairs on the central atom? Do you have any lone pairs on S? Yes, we do. Here it is. That's E. So therefore, we have AX2 E, or E1. I'll just be consistent with what you have on the sheet right here, because it says AX2E1. Here it is, AX2E1. You can either call it bent or angular. Either one is fine, but this is the structure. Now, you do not have to draw the like a line to the lone pair like it's shown here. I know this can be confusing. You can just put the lone pair on the top. Watch how I'm going to show you. So this is called angular or bent. We're going to use bent. And for the angle, we're just going to say it's less than 120. So watch. Here's how you draw it. Put the S, and you bend the angle at which the oxygens are, the sulfur is attached to the oxygens. So this is bent right here. And this angle right here, right here, right there is less than 120. So let me show you. Here's SO2. Should not be showing the two double bonds. I'm not sure why, but don't worry about it. Here it is. But you can see that the angle is about 119 instead of 120. Why is that? Very simple. This lone pair is held loosely. It's better, lone pair is held better by 2 atoms rather than 1. So that's why it's kind of like pushing the other ones, the other domains, these two double bonds down. Okay, next. So we did 2 domains. 3 in this case. So we are basically right here. Now we're going to work on the tetrahedral ones and the other ones. Okay. So if I have C, well, we did CH4. Let's do SI F4. Okay. SiF4. Si has 4 valence. And you have 4 Fs. Not as, here we go. Yep. So this is 28 plus 4 is 32. Okay. Si is central. Put 2 lone pairs on each side. So that's 8 for each fluorine. Okay. Do we have, is each fluorine happy? Yes. 8. Is silicon happy? Yes, it has 8. 2, 4, 6, 8. Okay, let's do the axe method. A, this is A. X, 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 and X. Do we have any lone pairs on Si? We do not. So therefore, we have no lone pairs. So you have AX4. Okay, let's go to our sheet. Here it is. AX4 is tetrahedral, the ones we talked about at the beginning of the class. So to draw this, you would do it this way. Si, F on the top, F at an angle here, and the wedged and the hatched line. Oh, yeah, see. Okay. AX4 is called tetrahedral. Tetra means 4, remember? Hedral means face, 4 faces. And the angle is 109.5, most important angle. Okay. Next, we did ammonia, so we did the structure. So I'm just gonna jump to the structure. The structure of ammonia looks like these. For a lot of the, like this one and water, maybe I'll spend a little bit more time on drawing some of these, but by now we should be, like I said, good with Lewis structure. So ammonia looks like this. Okay. Axe method. A, X, 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 and this is E. So we have AX3, E1. Okay, let's go to our sheet. AX3, E1. Oh, here it is. Here it is. Trigonal pyramidal. Sometimes called trigonal pyramid. So to draw this, you have to do it this way. You have an N. Okay, it's basically like the tetrahedral, except you remove the top and you put a lone pair instead. So here's the lone pair. And that angle is less than, it's actually less than 109.5. All the angles around it are less than 109.5. Okay. That's it. Now, it might say to you, this here, 28, that's just that's in you know how you have degrees and minutes. I'm not sure if you're aware of that. You have 60 degrees and you have degrees and minutes. So this is again just simply means that 28 means you have this many minutes, which is half, so 0.5. So don't worry about the 28, just write 109.5. Okay. Let me show you how it looks like here. Here is NH3. As I told you, trigonal pyramidal. It looks like a pyramid. Right here, and that's the lone pair. It's less than 109.5 because it's loosely held, so it's pushing down on them, on the other angles. Here it is. Okay. H2O. Structure looks like this. The angle, so this is A, XX, and you have two E's here, two lone pairs, so that's two non-bonding pairs. So you have AX2E2. Okay, let's go and find what's AX2E2 is called. Here it is, bent. We're going to use the word bent. Bent, bent. You put the lone pairs usually there at an angle. And I could have bent more, but this case, that would be less than also 109.5. It's about 1.104 actually. So it's less than 109.5 for just to make it easy. So where's water? Here we go. That's how water molecule looks like. Here's your lone pairs and then the angle of those bonds is bent right there. Here we go. So we're going to need more space. So push this down. Okay, now we're beginning with a bigger one. So we're going to go here. We're going to do about three more, I would say, 3 or maybe the most 4 more. And we'll be finished with that part. So let's begin. We did this one before. We did PCL5 or BBR5, whatever it is. We drew it last time on the last lecture. But anyway, P has 5 valence and you have 5 CLs. So that's 5 times 7. So that's 4. So remember, with this, you can have, starting with these next ones, you can have more than 8 valence. Okay. All right, where did this come from? All right. So we have P. All right. I'm not sure what happened here. Okay. Luckily, in organic chemistry, you're going to learn a quick way of, rather than just, those lone pairs are going to be implied, so you don't have to worry about them. But in this case, here we still have to, just because we're learning this, beginning to learn this. So A 5x's. Do we have any lone pairs on A? Nope. So you have AX5. AX5 is trigonal bipyramidal, the one we examined before. So and the angles for these are 90 and 120. The angles are 90 and 120, as you'll see here. Okay, here's the 120. And 90 is here. And again, it's trigonal bipyramidal. Okay. So what I'm going to do, what I want you to do for the next ones, I'm going to write down the formula, and I want you to pause and draw it and kind of really work it, solve it, and then verify with me. You'll see what you did. You can actually kind of diagnose if you didn't do anything, something correctly. So let's do SF4. So pause and solve the whole problem. So you should pause now. Okay. S has 6, and you have 4 Fs, 4 times 7. So that gives you 34. Okay. So far, how much do I have? How many electrons do I have? Count. 8 plus 8 plus 8 plus 8 is 32. So you have 2 valence electrons. Those are your leftovers. Where do they go? On the central atom, right here. Remember, they can take more than 8 because they're in period 3 and beyond. Okay. A, X, 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 and this is, of course, E. So we have A, X, 4E1. Okay, let's see what this is called. AX4E1 is called seesaw. Seesaw right here. Very good. Okay, why do you think it's called seesaw or sawhorse? If you recall, I don't think they have them anymore at the playgrounds or at the parks, but they used to have seesaws back in the day. They may have them somewhere. But seesaws are fun games where, you sit on one side, the other person sits on the other side, and you guys just move up and down. Here it is, seesaw. Up, down, up. That's why it's called a seesaw right here. Fun. So the angles are less than 90 and less than 120. So here it is. It's on your sheet. Okay. Do 2 more, and the other ones are just they follow. So let's do SF6. So you should work on SF6. Remember, we're here. There's obviously T-shaped other ones, but again, be able to just follow the same method. Okay, SF6. So you should pause now. Okay, you have S, that's 6 valence, and you have 6 F of fluorine atoms, so that's 6 times 7 is 42. 42 plus 6 is 48. S is central. Okay, so you know that they each have an octet. This is A, X, 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 and X. So this is AX6. This is called, okay. All right, I don't know why this is not moving, but if you can, I can't move this, not sure why. Let me make it bigger a little bit. Maybe you can see it that way. All right, here it is. That's called octahedral. Again, it has 8 faces. And the angles are 90. Okay, so the last one. So work on this one. You should pause now. So Br has 7. And we have 5 Fs. So that's 7. 5 times 7. The 35 plus 7 is 42. Br is central. Okay, let's do the X method here. A, X, 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 and X. So that's A. Okay, we're not done actually. Wait, I forgot to check here. We'll keep the X's for now. Okay, so check how many electrons you have so far. You have 8 times 5 is 42. You have 2 electrons left over. 2 valence electrons left over. Because you used 4, so they go here. That's your E. So that's AX5E1. Very well. What's the name of this? Let's go. Square. Okay, this is in the way. Here we go. Square pyramidal, AX5E1, less than 90, 90 above here. And then let's see how it looks like. All right. Why is it called the square pyramidal? Here's why. I've always, my philosophy of that, of learning in chemistry or in science is really similar to other disciplines, is you have to understand what the definitions mean. So square means it has a square base. You see the square? And it looks like a pyramid. Here it is. This is the pyramid. I guess in your so you can see that this is maybe a pyramid right here. And you have the lone pair. All right, you can have, you should be able to verify other ones. You have enough problems in the homework. So you should be able to do EXEF4 and verify that it's right here, square planar. I'll tell you why. Make sure you correctly predict the number of electrons. You're going to have XE, and you have 4 Fs. XE has 8 valence, and then 4 fluorines, each is 7. 28 plus 8 is 36. Now, look, when you do enough of these problems, you're going to develop the pattern. It's going to come really naturally to you. I'll tell you why. You know by now that if you have outer atoms, each is going to have 8. So meaning that you see how this fluorine has 8? Okay. So if you have 32, that means you have 4, right? 4 of those atoms. The more electrons you have, those are going to become lone pairs unless you have more atoms. So develop that pattern here. You know that 32 are going to be used for the fluorines, and then you have 4 more. Those are going to become lone pairs. So here we'll just draw it. So XEF4 looks like this. You give them 8. And you put the other lone pairs on here. This is going to be A, E, E, X, 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 and X. So that's AX4E2, which is square planar. Why is it called a square planar? Here's why. It's in the plane of the paper. Notice how flat it is. Those lone pairs are above and on the top and below, and it has a square base. That's a square right here. Okay, do enough of these. The next video, make sure you're good with that, because the next video is going to be on a more involved theory. And then we're going to wrap up really things at the end of this, and at the end of video 2, with organic structures and being able to relate the geometry and hybridization, pi and sigma bonds. So that is all. Thank you for watching.